Good afternoon. I am Kevin Ackerberg.
I'm Spencer Allen.
And we will be discussing our project Husker Scope 3.0 this afternoon.
Do we have, the keyboard, there we go. Sweet.
A bit of background. We are working for the UNL School of Computing. This application is intended for School of Computing students primarily in the course CSCE 436, Advanced Embedded Systems. This app aims to provide a means for students to test and validate their designs without the need to purchase expensive lab equipment or go to an electronics lab. And it is actually used by all students all over the world beyond this institution in electrical and computer engineering. A bit of background on our sponsor team. We have our project manager, Bill Browning, our tribe lead and product owner and sponsor, Professor Jeff Falkinburg, and also our industry coach Isaac Lean. All three were invaluable members of the Husker Scope 3.0 team, and we do appreciate all of the hard work they put in to assist us in making this a reality. This is our development team for 3.0, as we already introduced ourselves. Our other developers are Luke Whipple, Matthew Curtis Thomas, Adam Kemerath, and Chris Bayless. We had a good mix of software engineering, computer science, and computer engineers for this project. This is a hybrid software and hardware project, and the different disciplines definitely helped a lot in making this a smooth experience. Okay, so this is the third iteration of this project. Husker Scope 1.0 and 2.0 teams created a web and mobile application. It includes functionality for the following pieces of lab equipment: a dual-channel oscilloscope, dual-channel function generator, dual-channel spectrum analyzer, and an AM/FM modulator. Excuse me. The goal for 3.0 is to expand upon this functionality. We wanted to add in an 8-channel digital logic analyzer, and we also wanted to create an FPGA-based hardware interface for the application, increase the sampling rate, and extend the frequency range beyond the typical range of 20 hertz to 20 kilohertz, get high-frequency signals. This FPGA device is meant to communicate with the app wirelessly via Bluetooth. And this app would make Husker Scope a more robust application for students to use and allow them to take measurements of physical circuits they build in the lab. Previously, the app was constrained to just taking in signal through a 3.5 millimeter audio jack or some other audio input. A brief rundown of the solution we present on the software side of things. This is a screenshot of the robust logic analyzer page for the web and mobile applications our software team was able to develop. We have 8 channels of input, zoom and scrubbing functionality built in. The page was adapted to be compatible with all of our platforms. We are on iOS, Android, and web. And the user is given the option to use the microphone input on their device in the absence of the hardware interface. So if they do not have the physical PCB, Spencer will elaborate on that in a bit, they can just use the mic input and still get use out of this page. This is an animated view of kind of the feature set of this page. The software team wanted to, we collectively wanted to make this as intuitive and usable as possible for any user looking to measure some digital signals. And all aforementioned features you can see are demonstrated here. I'll now hand it off to Spencer, and he will elaborate on the hardware side of Husker Scope 3.0.
All right, thank you, Kevin. All right, so here we started with the hardware section. We were able to leverage a Xilinx AMD-produced CMOD F7 FPGA and an ESP32 to create a hardware prototype to initially test, as you can see on the right. It's a hardware stack with solderable breadboards put together to create the prototype. This hardware interface is the bridge between the physical circuits and the web app and phone app. There are 8 pins of logic, or 8 digital pins for the logic analyzer there, and 2 B and C connectors for the analog connection to the FPGA to send the signals to the Husker Scope. Here are some break-apart views of the actual hardware stack. This view contains the FPGA. You see the digital pins, and then this view has the ESP, which we are using for its BLE purposes, which has a bus going to it for power and UART. Right here is the actual analog circuitry for this. We wanted to be able to take in 5 volts for the ADC, so we can measure 0 or plus to minus 5, and the board itself that we were using could only accurately do it from plus to minus 1 volt, so we had to leverage some circuitry, some op amps, a bunch of just electrical engineering stuff to get it to send a signal that we're able to read with FPGA on the board and then transfer all the way through. Based off of that prototype, we were able to develop a PCB design, which you can see here. This is just the blank PCB that we received. It has a space for the ESP, the FPGA, and all the analog circuitry on one flat, relatively small unit branded with our logo. Here is the constructed one with the BNC connectors, the LA pins, and all of the analog circuitry, ESP and FPGA, bottom view, and another side view.
More finished and polished product.
Mm-hmm. This is what the end user would receive.
Yes.
Here is the basic flow of how data gets to the endpoint. So you start off with your circuitry, you connect either the BNC connectors or the logic analyzer pins. Those feed into the FPGA, and then it takes it in, does some processing, stores it, and then sends it over a UART to the ESP32, which then stores that in a buffer, then sends it out in packages to the final end result, which they are able to display on the endpoint.
Yep.
And some values and highlights. This project was great in expanding the functionality of the app and learning how to interface hardware with software all the way through, explore libraries, do a lot of research, and figure out what is going to be the best solution for the Husker scope to continue with in the future. We added in a logic analyzer to allow the students to analyze digital signals, along with
wireless.
Wireless
Communication. This, going back to the signal flow diagram, we aim with this project to replace having to buy 4 or 5 different pieces of lab equipment with this one $200-ish board and a cell phone. And that would allow an electronic or an EE or CE, electrical engineering or computer engineering student, to realistically do all the lab work they need to do from their dorm room. And a couple takeaways that we had. So we had a hardware team, a software team. The hardware team learned a lot about the life cycle of FPGA and hardware development and how it differs from more traditional software development. This was a really good learning process, especially for us computer engineers. This is our bread and butter, but actually doing it hands-on and getting a product to release was certainly very rewarding and very educational. The software team definitely learned a lot about the benefits of communication and pair programming. Productive discussion drove a lot of development in the right direction. And similarly on the hardware team, but especially software. Yeah, thank you for your time. Thank you for listening.